Over the last 250 years, we have, in effect, conducted the largest science experiment in history. Since the advent of the Industrial Revolution, we have burned over 1.4 trillion tons of carbon into the atmosphere. It has changed life on Earth as we know it, especially in the Arctic. The melting of the world's snow and ice has now triggered multiple climate tipping points, threatening the very existence of life on Earth. Yet this disturbing future need not be set in stone. We have long had alternatives to fossil fuels, but more recently, we have actually discovered how to pull carbon out of the atmosphere, giving us a chance at reversing climate disruption. If we are able to reverse climate change in time, it would be an unprecedented achievement in human history. But the clock is ticking. Scientists say we must implement these solutions immediately. At this critical turning point, we must give a voice to the impartial experts who have presented us with the facts they have spent a lifetime to uncover. It is their time to be heard. They are the scientists, researchers, and innovators who have found the solutions to preserve the very life of our shared world.
There's a couple different projects that require manual sampling. So one of them is the long-term CO2 record. And the way it's set up, you still need a person to come physically take the sample every Tuesday. I'm the person that gets to go in the snowcat to take the measurements. We want to keep that long-term record going the way it's always been taken.
Monitoring and tracking what we're doing to our atmosphere is a serious and difficult endeavor. For the last 50 years, dedicated researchers from around the world travel weekly to the same locations, taking samples of greenhouse gases that cause climate disruption.
So we're at about 11,500 feet on Niwot Ridge, in the Front Range of the Rocky Mountains in Colorado. And this is NOAA's long-term CO2 sampling site here. It's the third longest in the world. So these are the flasks that we're going to use to collect our sample made out of glass. And after we're done today filling them with air, we'll ski them down to our office, and then we'll take them down to NOAA's office in Boulder where they get analyzed along with similar flasks from all over the world. The reason we do it up here, and a lot of the sampling sites are high up in the atmosphere, is the air up here is well mixed, so you're getting a good sample of the whole atmosphere. There's a little inlet on the roof. When I turn on the pump, it's going to suck the air into these flasks. This is actually the whole carbon cycle and greenhouse gases, and CO2 and methane are the big ones. When they took the first sample in 1968, it measured 322 parts per million. And we don't know what this sample is going to measure yet, but it's probably going to be around 408. So it's a little bit of an increase. And now I'm just putting everything away and getting it ready for next week's sample.
One of NOAA's missions since its inception was to measure carbon dioxide in the atmosphere and other gases that affect the carbon cycle. 2 samples are collected every week from around the globe. So we're looking to see how these gases change with time. And the way to do that is to continuously collect samples. Currently, we have about 60 locations. Most of the samples are collected in remote areas, away from population centers. And we measure on this set of instruments for 6 gases that affect the carbon cycle. Those gases are carbon dioxide, methane, carbon monoxide, molecular hydrogen, nitrous oxide, and sulfur hexafluoride. This system runs 5 days and 5 nights a week, 24 hours a day. So what I'm doing right now is putting the air samples on the manifold and start the measurements. And then I can walk away.
I lead NOAA's Global Greenhouse Gas Reference Network. The aim of the Global Greenhouse Gas Reference Network is to provide data that are fully calibrated, carefully quality controlled and documented. Data that will still be fully credible 100 years from now and longer. So that as climate change is happening now and in the future over the Earth, there will be information for scientists that they can really trust so that they can diagnose what actually happened and how climate change actually happens, how it works. So modern CO2 measurements were initiated by Dave Keeling of the Scripps Institution of Oceanography. Around 1956, he started measuring along the West Coast. He saw that during mid-afternoon, wherever he was, he found pretty much the same concentration everywhere. And so it got into his head the idea that maybe there's something that we can call a background concentration. He started continuous measurements then at Mauna Loa, island of Hawaii, and on the coast of Antarctica. The last ice age, at the end of that glaciation, from 20,000 to 11,000 years ago, CO2 increased by about 80 ppm. From 200 to 280, roughly. It was very slow. It took 6,000 years for CO2 to climb 80 ppm. 6,000 years. In pre-industrial times, so before 1850, CO2 was close to 280 ppm. And now, of course, we see 2 ppm per year. That increase was due 100% to human activities. Oh, the spike that we now see compared to most geologic history, I call it an explosion. It's right, instantaneous in geologic time scale.
Carbon has increased dramatically since the Industrial Revolution. But what does that actually mean for all of us? What we have learned is that excess carbon creates climate disruption. It changes the weather patterns and life support systems upon which society depends to survive.
We have always known that there's a toxicity associated with fossil fuels, but we'd always thought that it was basically a toxicity that would affect humans, or other, individual life forms. It's really only in the, within my lifetime, certainly, that it has become frighteningly apparent that the accumulation of carbon in the atmosphere has caused it to warm up. This greenhouse effect, this toxicity, impacts the life systems of the planet as a whole. And, once I got that back in the mid-90s, I had to start talking about it, and we've been talking about it ever since.
When we talk about dangerous planetary warming, we're referring to something akin to a 2 degrees Celsius, that's about 3.5 degree Fahrenheit warming of the planet relative to pre-industrial times. That is where we start to see some of the worst and potentially irreversible impacts of climate change. Substantial melting of the ice sheets and associated substantial rise in sea level, permanent droughts in mid-latitudes, and the list goes on. Well, catastrophic, would be we melt the major ice sheets, the Greenland ice sheet and the West Antarctic ice sheet. As all the major coastal cities of the world are flooded, you've got less land, you've got environmental refugees, some people leaving those regions, people leaving the tropics because it's getting too hot for human habitation. It's getting too hot for agriculture. Crops in the tropics will decrease dramatically in their productivity. In short, you're looking at a world with less land, less food, less water, and more people. And that's a recipe for a national security disaster.
I work on the carbon cycle, tasks that I've taken on for more than 30 years. And truth be told, I figured we would have done something about this 20 years ago and I could be off doing something else, but I'm still doing what I'm doing. If you think about the relationship between carbon dioxide and sea level, there's a couple of interesting points in that relationship. One of them is when CO2 goes up to roughly 400 parts per million. That is warm enough that we melt off chunks of Antarctica, chunks of Greenland. And those chunks are the chunks that are what we call marine base. So the base of the ice sheet in West Antarctica is below sea level, as it's pinned to the sediments. And once it starts to melt, it's one of these freight trains. We don't know how this thing is going to stop. And we're dangerously at that point right now. The other threshold is somewhere around 600 to 700 parts per million CO2. That's warm enough that there is no more ice, land ice on the planet. And you have about 80 meters higher sea level. We are on our way to 600 to 700 parts per million. But I think that's one of those interesting threshold moments in our relationship with the planet, where are we going to push the climate system so far out of balance that we threaten the melting of all land ice?
Yeah, it has changed. Icelandic nature is experiencing change because of climate change. This is quite visible in the south coast, for example. Our largest glacier, Glacier Vatnajökull, or water glacier, if you translate it directly, has also retreated quite a lot. There is one very interesting observation that everybody noticed when they drive the south coast now, and that is that they drive over the longest bridge in Iceland, almost 1 kilometer in length, and there is almost no water under it. So you think, okay, why building such a big bridge for almost no water? Well, this is just climate change. The river changed its course is because of the retreat of the glacier. So now we have this sort of monument, a symbolic thing of the past.
The Arctic is a profoundly different place right now. In the Arctic, the impacts of climate change are the most extreme. What scientists are finding is that what happens in the Arctic has major impacts for the rest of the planet.
I'm working with measuring greenhouse gases at the Arctic location and understanding how the greenhouse gases are changing over time. I am concerned about the increase of temperature in the Arctic and the impact this might have on all the Arctic systems. But what I think is extremely important to be aware of is that with the sea ice reduction we have now and all the other changes, you might change the whole weather system, and this has global impact. We know that the changes that we see in Arctic does not only stay in the Arctic.
I've been working on sea ice for the last 50 years, pretty much, and the whole Arctic has changed so much in that time. Loss of ice, loss of not only the loss of area of ice, but the loss of the appearance of the great ice fields of the past with huge pressure ridges, very, very thick ice, really dramatic ice scenery has all gone. Last month, I was up in the Barents Sea on a research cruise in a region where normally you would have quite a lot of multi-year ice. We couldn't find any multi-year ice. So the ice was all very thin, 30 centimetres thick. The Arctic Ocean is no longer a continent of ice, but something that becomes just water in summer. So it's a huge loss as far as beauty is concerned, but also as far as the physics of how the planet operates. The ice is disappearing because the climate's warming. That's pretty obvious that will happen, but there's much more to it than that because, in fact, you have many other feedback mechanisms going on which cause the effects on the planet to be far worse than just the retreat of the ice. So the Arctic's warming up 3 times faster than the rest of the world, and the temperature difference between the Arctic and lower latitudes is getting less. And that means that the jet stream is getting to be weaker. And as it gets weaker, it goes from being almost a straight line to becoming big lobes reaching up north and south. And when you have a lobe like that, it means that polar air can come down to lower latitudes than it normally reaches in one sector, and then in the sector to the east or west of it, you've got warm air going up north further than it should do. So you're getting bizarre weather extremes, which of course everybody's been commenting on. And the trouble is, where these air masses are causing such extreme changes happens to be the latitudes at which you have the maximum food production. Suddenly our ability to feed everyone is being affected by these polar changes. You can't take that amount of ice away without affecting so many other things.
The impact of our actions are starting to hit home. Scientists' predictions are now coming true sooner than expected. We are tragically suffering through severe storms, droughts, floods, and fires that are progressively becoming more intense and more unpredictable.
Fires started almost simultaneously in multiple places. Over 7,000 structures were destroyed and about 3,000 homes. I think at the height in the early days of the fire, maybe about 100,000 people were evacuated. It's a collective trauma.
Sounded like a war zone, looked like a war zone. You know, they talk about the Hanley fire. It took a day to get here. It burned about the same footprint, but it took about a day, burned less than 200 structures. This fire started at night, made it to Santa Rosa in 4.5 hours, and there's no comparison other than the footprint. Cal Fire Incident Management Team came here to help run this incident. And he just shook his head and said, man, I've never seen anything like this. I've been doing this a long time. So that's not terribly comforting, but that's where we're at right now. If we keep having these wind events, how do we protect our citizens? How do we protect our infrastructure? What are the things that we can do to make it as good as possible? We've been through 4 or 5 years of drought. That drought stresses all the brush, all the trees, and you know, the winds at Geyser Peak on one of the weather stations was clocked at 108 miles an hour. And I don't know what you do with those kinds of winds. When something catches on fire, it's all you can do to try to figure out where it's going and how fast it's going to get there.
I never would have thought the fire would come out of the hills and run the flats in Santa Rosa. I really didn't. Cars were being flipped over. There were shoebox chunks of, you know, embers that were being carried well ahead of the fire. You'll see there's some trees where all the limbs are they're snapped off. They're not burned off, they're snapped off.
These natural disasters are so common now that people know what's going to happen to their community. It's not like a matter of if, but when. It is a wake-up call to everyone that climate change is here and that you need to plan for it.
Climate disruption is causing a rise in extinctions today. But this isn't the first time. Scientists studying geological records have shown there is a connection between spikes in carbon and the past 5 mass extinctions. There is a natural law that the carbon cycle affects the fabric of life. Every time there has been a massive increase in carbon, the web of life weakens and sometimes collapses.
I've been working on the way in which the carbon cycle is associated with the occurrence of mass extinctions and whether the carbon cycle can undergo instabilities associated with it. So the carbon cycle is where life and the environment interact. You can think of it as one grand loop between photosynthesis, which is a process that takes carbon dioxide out of the atmosphere and converts it to oxygen and plant matter or organic carbon. And then the back reaction of the loop we call respiration, which is the process by which we convert that plant matter to carbon dioxide. The grand loop of the carbon cycle takes about 100 gigaton of carbon out of the atmosphere and oceans every year, and it returns it each year. So this is 100 gigatons out, 100 gigatons back in. But what we're contributing is on the order of about 8% from fossil fuel burning. It's an 8% increase compared to what is normally going back and forth in a year. It turns out to be more than what volcanoes are putting into the system.
The planet is constantly in the process of rebalancing its cycles, like its water cycle and its nitrogen cycle and its carbon cycle. You've got to think of it as it's in constant flow. And part of the planet's doing that, you know, was to take all the carbon that was in the dinosaurs and land plants and press that into eventually oil and fossil fuels. Over long periods of time, it was sequestered, and we're a young species. And we were curious, and we dug up the carbon that had been sequestered by the Earth. And we burned it, not knowing it was like burning furniture in a house with its windows closed. So what's happened is that the planet is reeling from that. There's an excess of carbon up in the atmosphere. What it's doing is causing that living conditions here on Earth to go out of bounds. So as a biologist, when I look at climate change, yes, I look at rising seas and melting polar caps. Those are evidence for me. But when we begin to look at what's happening to the biological organisms in response to the warming trends, they are already on the move. They're moving towards the poles to get cooler. They're moving from the lower mountains up in elevation, meaning their ranges are moving. They also sometimes move without their helpers. A plant will move north and its pollinator won't make it. This is called, in our bloodless language of science, it's called ecological disruptions. So for me, if we change the very conditions that gave rise to all of this, and to us, it's going to get crazy.
When the carbon cycle is unstable, it moves into a realm that we don't understand. Going back into geologic time, is that occasionally there are these essentially bursts within the carbon cycle in which things change. One of them, which is widely known as the Paleocene-Eocene thermal maxima, 55 million years ago. And others, which are decidedly worse, they're destructive or catastrophic events, they're mass extinctions. The worst of them, known as the end Permian extinction. So that's the historical record, but what we're doing to the carbon cycle now is another kind of problem, because now we know what's going on. We know that we have been adding carbon dioxide as a consequence of fossil fuels. And then the question is, does that risk engendering the kind of burst that we've seen in the past that could create what I would call an instability in the carbon cycle? That is one in which small changes become bigger changes. That's a precise scientist's definition of catastrophe. But when you get down to the individual level, losing one's home to a flood is a catastrophe.
We can still avoid breaching that dangerous limit of 2 degrees, but if you do the math, with each passing year of relative inaction, it's getting more and more difficult to limit our carbon emissions and remain under 2 degrees Celsius warming.
Je regarde la salle. Je vois que la réaction est positive. Je n'entends pas d'objection. L'accord de Paris pour le climat est accepté.
We know we have put too much carbon into the atmosphere, but how much is too much? Scientists have figured out what that amount is and have created a carbon budget that will create a margin for life. This budget tells us where we are now, how much more carbon we can burn, and how much needs to be removed in order to sustain life on Earth as we know it.
I would say the major challenge is indeed dangerous climate change. And if we want to avoid dangerous climate change, so then we have to accept that the atmosphere is, for humankind, a limiting disposal space. So roughly we can emit 800 gigatons CO2 into the atmosphere in this limiting disposal space. And if you take into account that over the last 5 years we have already used 200 gigatons, so this basically means that over the next 2 decades we have exhausted the limiting disposal space.
So in Paris it was very important that the whole world and the whole world leaders agreed on limiting temperature increase to well below 2 degrees. So that's a kind of safeguard line, and it's very important that more than 100 nations stand behind it. So imagine the volume that is in this ball. That's a kind of symbol for the CO2 that is still in the ground in terms of coal or in form of oil and gas. So this is the amount of carbon. And if we want to limit the temperature to 2 degrees globally, we may only emit this little amount of carbon into the atmosphere. And to see that we have a lot more of carbon still stored in the ground that we can emit in the atmosphere when we want to limit the temperature to 2 degrees. So therefore the question is, how does it fit together?
So, and now for the next 20 years, this is an enormous important time span to transform our economies, to decouple economic growth from emission growth. And by mid of the century, we need zero emissions. And after 2050, we need even negative emissions. The carbon clock is just informing people where we are now. What is the pathway, how we exhaust the limiting disposal space of the atmosphere. And this is a huge challenge for humankind.
Science tells us that our current climate crisis is a problem we've created, but it is also a problem we can fix. Not only do we need to stop emitting carbon at the current levels by switching to renewable energy, but it is also critical to pull carbon out of the atmosphere. Climate change can be reversed if we act now. Recently, researchers have figured out what solutions can draw carbon down, getting us back to pre-industrial levels.
There's only 2 things you can do about the atmosphere. You can either stop putting greenhouse gases up there, or you can bring CO2 back down. That's it. And you can do the first one by conservation, energy efficiency, and clean energy. And the second one through photosynthesis, whether it's on land, on farms, on forests, phytoplankton, kelp in the oceans. There's only 2 things you can do. So that actually sorts it pretty simply. And in the past, what has been done in terms of solutions is that it's focused on energy. Energy, energy, energy. And the reason for that is understandable. So it makes perfect sense to say, well, let's stop putting that CO2 up there. Accepting that in the process of emphasizing clean energy, renewable energy, solar, wind, etc., it's sort of occluded the rest of the solutions. The purpose of drawdown is to see if the 80 solutions that we had modeled would scale to the point where we could reverse global warming within 30 years, going from reduce to reverse. You bend the carbon curve, what drawdown shows is that we have choices. And that if we increase the rate that we're scaling some of the solutions, then we can achieve drawdown at 2050. And if you say the odds are long, I agree. They're long odds. I'll take them.
My name is Linwood Gill. I'm the Chief Forester for the Usal Redwood Forest Company. Usal Redwood Forest is a community forest. It's owned by a nonprofit, the Redwood Forest Foundation. It's a 50,000-acre forest which is dedicated to managing the forest on a long-term basis for the economic stability of the community, as well as restoring the forest habitat, restoring the fish habitat, and also for sequestering carbon. And carbon sequestration is a main part of our operations right now. Carbon sequestration is an important part of combating climate change. The Usal Redwood Forest is a very young redwood forest, and redwoods can absorb more carbon than any other forest type on the planet. Redwoods store carbon by absorbing carbon from carbon dioxide out of the air into its needles and stores it into the bole of the tree, the trunk, or the roots, the branches. To my knowledge, this is one of the largest carbon projects in the country. Yes.
I am the biochar project manager for the Redwood Forest Foundation. We're sort of at a perfect storm right now in California, where we have over 100 million dead trees in the Sierra, and we need to do something with that.
We have what is called the western pine bark beetle, which makes its living by feeding on ponderosa pine and other trees as well. And these beetles have been around for thousands of years and have lived in harmony and balance with the trees. But unfortunately, because of climate change and because of the long drought, millions of trees are very weak and have difficulty defending themselves against the beetles.
Biochar can definitely be one of the ways that we address the beetle damage in the dead and dying trees in the Sierras. Biochar is essentially the form of charcoal that is suitable for use in agriculture and in helping to build more healthy soils. When you pyrolyze woody biomass particularly, about half of the carbon that is in that woody biomass can be saved as a residual charcoal. And biochar is very much like coral for the soil in that it can hold nutrients, it can hold water. It's more of an architecture. It incubates life. You're saving about half of the carbon that's in that plant and then can put it to better use and sequestering it in soil for great benefit to agriculture. We have all this biomass that we have to do something with.
They are a fire hazard, and as you know, right now we have something like 10 fires in California. And by producing biochar, we can return some of that material back into the forest in a safe manner, or we can take some of that biochar and take it down into the Central Valley, which desperately needs water savings. And one of the prime benefits of biochar is that it can help to retain water in soils.
If we put biochar in just 10% of the world's soils, we'll actually sequester 29 billion tons of CO2. 29 billion tons, that's on 10%. And that's using only quote-unquote surplus waste material. So that's significant.
And then we have the carbon offset credits. And to keep those carbon credits coming, we have to employ workers to do our forest inventories, to work with the carbon verifiers to make sure the carbon that we say is on the property, and then is maintained into the future. I'd like to think that we're a model that others can join in and do the same thing that we're doing out here. This isn't rocket science. The carbon storage as we move into the future is huge, and we need more, larger older forest, intact forest that we know will never be developed and can continue into perpetuity.
I'm Kate Scow, and I'm a professor in land, air, and water resources at University of California, Davis. And I'm a soil microbial ecologist. So the carbon cycle on a global scale involves aquatic systems and terrestrial systems. So soil is a very important part of the terrestrial systems. Soil actually contains 2 to 3 times the amount of carbon that is in the atmosphere. Soil is the place where primary productivity is supported. That means all the vegetation that grows, that fixes CO2 through photosynthesis from the atmosphere. What miraculous, like creating mass here on the ground out of what? Air? It's like still amazing to me. That productivity brings all this carbon in. The plant fixes the CO2, it dies, it falls onto the ground, and all that plant residue now enters into the soil carbon cycle. It's way bigger than the atmosphere, what is residing in soil. So organic farms obtain their nutrients not from synthetic fertilizers. The fertilizer is in the form of organic material. That could be cover crops, or it could be compost that's made of food wastes or yard waste or animal waste that you put in the soil. So in organic systems, you may be putting up to 8 times as much carbon into the soil compared to a conventional system. So it's like part of it is really basic.
Climate change gives us an opportunity to really behave differently on this planet. We see what we can do at our worst, and now the question is, if we were to consciously be a part of the healing, it'll unleash, I think, our creativity. You realize, oh my gosh, I have a backyard. Oh my gosh, I have a park near me. If we were to see ourselves as helpers who could help the helpers heal this planet, that is so much better than seeing ourselves as disruptive toddlers with matches. You begin to realize that all of us are somehow connected to little bits of the solution.
This is right now, we live and direct at my mentor's house, the OG, the organic gardener, Ron Finley. I'm more inspired to always come here and learn and figure out different ways of how I can actually utilize a small plot of land to grow the most that I can. Culinary climate action is basically what I like to see when I'm growing the food, and it's basically taking all that carbon out the atmosphere. It's pulling it in, and we also can see the fact that we can put it back into the soil. Not only as at the same time it's creating green jobs, you know, and also addressing things like diabetes and obesity in my community where I come from. You know, there's a lot of plots, there's a lot of city access, there's a lot of water that's available. This is really just it's a beautiful cause and effect. We're literally pulling out all the harmful poisons that we like literally just emit into our atmosphere. And the best way that you want to transform that is by growing some food, put it on the roof, put it in your windowsill. But we feel the heat rising. You know, being a farmer is being futuristic. There is no doomsday mentality. You have to actually plant water and think that you're gonna reap what you sow. So that's the conversation that I like to see. And, you know, when we're talking about transforming the climate, it's not gonna happen overnight, but you do have to start now. Now's the time.
My name is Bren Smith. I'm the owner of Thimble Island Ocean Farm.
and we're here in the Thimble Islands in Long Island Sound. And I'm born and raised in Newfoundland, Canada, high school dropout, and have fished all over the globe. I fished in Gloucester, up in Newfoundland, and then I was in the Bering Sea for a bunch of years. And, you know, that was the height of industrialized fishing. We were tearing up entire ecosystems with our trawls, chasing fewer and fewer fish further and further out to sea. So it was completely unsustainable. In fact, a lot of the fish I was catching was going to McDonald's for their fish witch sandwich. It really caused a wake-up call for a lot of folks in my generation. I was actually out in the Bering Sea, and the cod stocks crashed. And, you know, thousands of people thrown out of work, canneries shuttered, and it really taught me that you can build up an economy and a culture over hundreds of years, and if you don't protect the resources, an ecosystem collapse can wipe it out in a matter of years. And that's when we really begin to realize that issues like overfishing, like climate change, that they're not environmental issues for a lot of us that work on the ocean. They're economic issues. I mean, there's going to be no food, no jobs on a dead planet. When I realized this wasn't sustainable, I went on this search for sustainability. I remade myself as an oysterman. And what oysters taught me was that Mother Nature created these technologies millions of years ago designed to mitigate our harm. We don't need advanced technologies. Mother Nature has seaweeds and shellfish which sequester 5 times more carbon than land-based plants, filter 50 gallons of water a day per oyster, pulling nitrogen out of our system. I mean, my job as a steward of the ocean is to take Mother Nature's technologies and grow them. And it's pretty simple. So the beautiful thing about if you grow just restorative species is there's zero inputs. We don't need fresh water, we don't need animal feed, we don't need fertilizer, and we don't need land, making it hands down the most sustainable form of food production on the planet. So kelp is this beautiful seaweed. It's like the gateway drug to a new cuisine. It's one of the fastest growing plants on Earth. It soaks up 5 times more carbon than land-based plants. It's called the sequoia of the sea. But it's just the beginning. I mean, we're starting with kelp, but there are 10,000 edible plants in the ocean. Part of the plant we can turn into kelp noodles, but then this, which is biofoul, we turn into fertilizer, and we can turn into animal feed. If you provide a seaweed diet to cows, you get a 90% reduction in methane output. It's stunning, and cows, sheep, goats, have been eating kelp for hundreds of years. Hebrides Islands, Maine, all sorts of places. You know, the volume's stunning. We can do 10 to 20 tons of kelp per acre, 150,000 shellfish. Now, you scale this up. If you were to take a network of our farms totaling the size of Washington State, technically you could feed the world. If you took 5% of U.S. territorial waters and farmed in our style, you could create 50 million direct jobs and sequester the equivalent carbon of 20 million cars. Our farms also help mitigate acidification. The kelp creates something called a halo effect, which reduces the acidity in the oceans, which then allow our oysters and other shellfish to grow thicker shells and not be as susceptible to acidification. So I mean, climate change was supposed to be this 100-year sort of slow lobster boil. And instead, it's here and now. Luckily, as fishermen, we can transition to something that keeps that core and have the pride of helping feed my country. And that's just so exciting. I can be part of, you know, the army that's going to help hopefully save the planet.
If we put 10 units of CO2 in the atmosphere, 10 very large units of CO2 in the atmosphere, about 5 stay in the atmosphere, and about 2.5 go into plants, and about 2.5 goes into the ocean. So you've got an acidic ocean, so how do you deal with that? Now, nature handles this problem by making more shells, which is the marine snow idea, that little beasties grow in the water, they make calcium carbonate shells, those shells fall. The problem with that is the planet loves to operate on timescales of millions of years, and we don't. So the question becomes, can you speed that process up?
We have to investigate all our options. There are more experimental hypotheses that still need to be tested. One solution may lie in a microscopic community of life called marine snow.
So, fundamentally, what do we need? Well, we need this planet as it was. We have to bring it in the state that was 200 years ago. Higher concentrations of carbon dioxide, they increase acidity of the ocean. The oceans are losing their ability to capture carbon from the atmosphere. And we have to do something about it. We have to help these systems which cycle carbon between the atmosphere, between the plants on the land, and between the oceans. And with marine snow, it just needs a little help from us. The main products will be removal of carbon dioxide and the production of oxygen. What we can do is insert into the ocean very small, minute amounts of iron, but very, very little. So it doesn't have anything to do with that term fertilization. To give you a measure, we need altogether about 6 kilograms of iron for initiating this process on 100,000 square kilometers of the southern oceans. The cells form organic matrix, which is the foundation for the formation of the marine snow. It is then when the matrix appears, it becomes very attractive for cyanobacteria and heterotrophic bacteria, which colonize these particles and then actively grow. And then we just let them do their job because they can stay suspended for a very long period of time. We tracked these marine snow particles for more than 4 months. So they can float around and sequester organic matter, and when they become heavy, they simply sink down to the seafloor. The speed of this change and increase in the concentrations and temperature, we must act, and we can. I'm 100% positive that we can achieve reorganization of human activities to work together with nature and not against it.
Science has long proven we have existing technologies that work, and they are already being implemented. It's just become a matter of political will and scale. We need a multitude of solutions moving forward simultaneously. In order to solve this crisis, it is critical we move to 100% renewable energy now.
So the top 5 solutions, number 2 was onshore wind, and that wasn't a surprise. Onshore wind, though being much greater than solar, was a surprise to us. Solar was number 8 and 10, actually.
The sun is the largest resources we have. All the other resources pale compared to the sun. We have known that for a long time. We just never understood how to harvest it in an economic way. That's what's different now. Solar PV is in a stage where we're already lower than fossil fuel. Well, solar has come a long way. Carter in the 80s already installed solar on the White House. Reagan teared it down later on. And only in 2001, when Germany started to deploy solar on a large scale, we have been getting the benefit of economy of scale. Eventually, we will be able to power the entire electrical grids with solar and wind. And all we need is wind and storage and solar and storage. So if we want to power the entire United States with photovoltaic, we need about 30,000 square miles in area. That would give us enough to power all the power grids in every state of the United States. Well, Mount Signal is a project that powers about 70,000 homes in San Diego. The second phase, the power is going to be wheeled to Southern California. The price of electricity that we produce at Mount Signal is already lower than fossil fuels. It's also a price that delivers fuel price certainty to the utility. The price is flat over the next 25 years, not something that you get from any other fossil fuel energy. We have integrated so much solar in California already. 10 years ago, people would have said, no, that's not really possible. Well, here we are. Solar is covering already up to 25% of California. The ratepayer had no material increase in pricing, and we're still alive. All works. And we have been able to reduce carbon on the way there. Over the last years, we saw now utilities volunteering to buy solar. We see this mindset shifting. We still underappreciate the value that PV brings. People do not comprehend that in 5 years, we will have PV at much lower price. We will be able to dispatch it at night, and you combine that with wind, you get this paradigm where we are truly living in a 100% renewable environment. And this is feasible. We don't need any new invention for that. We know all the technology. We just need to make sure that the people responsible for the planning of resources, for the infrastructure planning, understand that this is a different technology and it will get cheaper over time.
Coal is coming back. Clean coal is coming back. 100%. My administration is putting an end to the war on coal. We're going to have clean coal, really clean coal.
It's difficult enough sometimes to communicate science to the public. Now you take that challenge and you add to it a concerted effort by fossil fuel interests and the front groups that they fund to pollute the discourse over climate change, to confuse the public, to confuse policymakers. We need to transform our energy sector, move away from fossil fuel energy towards renewable energy. Well, that's rather inconvenient for the powerful fossil fuel interests who have many millions of dollars invested in our continued addiction to fossil fuels. And they've fought tooth and nail to maintain that addiction, in part by attacking the science, linking climate change to that behavior, the burning of fossil fuels.
A question that we get asked a lot is, how do we know that the CO2 rise in the atmosphere is because of human activity? And the answer is that we leave fingerprints all over the atmosphere. And one of the fingerprints that we leave on the atmosphere is via what we call carbon-14, or radioactive carbon. So when we burn coal, oil, and natural gas, we leave an imprint on the atmosphere of what we call negative carbon-14, or less carbon-14. Because fossil fuels are so old, there's no carbon-14 left. It's all decayed away. We can actually measure very accurately how much fossil fuels we burn by measuring C14 in the atmosphere. It is nature's verification system that we have.
They persuaded enough people and sowed enough doubt that it's making it more difficult than in the past to actually get anything done about climate change, and that's really depressing.
And the fact is that the agenda that many of these fossil fuel corporations and those who are running them are engaged in is malicious in the danger it's creating and the havoc that it is wreaking on our planet.
So we've got a bunch of people who are literally profiting off the death of life on Earth. I think that some climate denial, particularly the well-funded climate denial that is being done by people who know better, rises to the level of a crime against humanity that probably should be prosecuted in The Hague.
While climate deniers have succeeded in delaying action, a much more ominous problem has emerged. Very recently, scientists have recorded increasing levels of methane gas in the atmosphere. Methane, a powerful greenhouse gas, has the potential to increase temperatures even further. Increased methane is a sign that we are reaching a critical tipping point. But where is it coming from? And how much will it accelerate climate disruption? Scientists are racing to find out.
So we are in front of the University of Wyoming Mobile Laboratory. We have different instruments inside that measure what's in the air that we are breathing right now. It's doing that in real time. And we are able like that to chase emission sources and plumes and understand where sources of pollutions are located, what activities are going on that lead to enhanced methane.
Inside of our lab, we have a couple instruments. We have a proton transfer reaction time of flight mass spec to measure volatile organics like benzene, toluene. And then we also have a Picaro cavity ring down to measure methane concentrations. We can see data from these instruments in real time due to an inlet we have up on our mast above the van, which pulls air in and feeds into our instruments.
So we found with aerial and road mapping that we have more sources of methane in areas where we extract the gas than we expected. And to really pinpoint where there are leaks of methane, you need to be very close to the sources. And the mobile lab gives us the flexibility to pinpoint where we see the largest leaks. The company has drilled brand new megapad, 22 wells in the middle of renewed urban development in Western Greeley. This is a site that had a lot of contention given its size and its location. So the local community, from what I've heard, is not really kept up to breath on what's going on at the site. There's a huge sound wall around the operation. And the state is not really maybe doing its best at facilitating the communication. We saw operations going on with a lot of flaring. It seems very large volume of gas. The yellow color of the flame tells you it's not complete combustion. So we are going to continue doing those drives to understand those sources, but also to track what the local population may be exposed to. So some oil and gas producing regions have such a large concentration of methane in the atmosphere above them that you can see it from space. And that's something that was described a few years back for the Four Corners region.
And that's really the key for us to be like detectives and map where we see the largest sources of emissions.
So in 2014, NASA scientists, in cooperation with NOAA, University of Michigan, and other scientists, identified a methane hotspot the size of Delaware in the Four Corners region. That methane hotspot is the largest accumulation of methane gases in the United States. This ranch, this spot that we're on, is approximately ground zero. If you were able to identify a middle for that Delaware-shaped cloud, it might very well be right here where we're standing. And they've closely identified the cause of that methane hotspot to be predominantly the emissions from drilling such as this site, as well as coal and other fossil fuels. So the methane hotspot is identified basically because of the technology that NOAA and NASA had following the advent of the FLIR cameras, which are the infrared cameras that let us identify the leaks and vents and flares that cause the methane hotspot to accumulate. You have to think of it in its full sense, and that is 60 years and more of leaking, venting, flaring, and careless practices here in the San Juan Basin, over 1 million acres, in total 30,000 wells, that have caused that methane hotspot to finally accumulate and stand as evidence of what natural gas drilling ultimately results in. People lose sight of the fact that the conventional wells created the methane hotspot and that they are a daily culprit. So this is a conventional natural gas well. This is very typical equipment throughout the San Juan Basin and many gas fields across America. This one is leaking pretty badly from some of the standard equipment that's on it. This just requires, honestly, a crescent wrench, a little bit of Teflon tape. Some attention will fix this leak. If I had a single wish, my wish would be to pull an investor in oil and gas here and stand them where I'm standing. Let them see that leak. Let them see that times 18,000 in the San Juan Basin, and get them to stop obstructing a federal rule that stays in place to protect my family, to protect taxpayers across New Mexico, and provide federal, fair, and equal protection across the western states. Let's get those guys out of the boardroom right here on this well location. Let them look at that leak that can be easily fixed. And when I found out that the EPA Administrator, Scott Pruitt, knew that the data had come in that methane leaks and the chemicals that come with them harm children to a greater degree than they did to me, I was just outraged that he would try again to roll back the federal protections for us. You know, if someone came onto my ranch with the stated objective of harming my children, it would be over my dead body.
$250 million years ago, sudden releases of methane produced kind of a secondary effect that finished off large chunks of life on Earth. And one of the debates right now is whether the methane that is buried in the Arctic, whether the methane that is, in the permafrost in the seas all over the world, how rapidly that will be mobilized and how destructive that mobilization will be.
The release of this ancient methane may lead to exponentially more warming. Will this methane create an apocalyptic scenario? This is a question scientists are desperately trying to answer.
I'm the director of the Center for Gas Hydrate, Environment and Climate. Here we have a team of 50 to 60 scientists working on understanding the impact of methane on the global climate system. This methane is stored beneath the Arctic Ocean floor in huge reservoirs at locations we sometimes know, but we often do not know very much about it. So we are applying here geophysical methods to quantify the methane hydrate reservoirs and also to see how stable those methane hydrates are today, but also in the future. Methane is one of the most aggressive greenhouse gases. Methane has, fortunately, a shorter lifetime. The Earth has a natural system for regulating input of methane from the ocean and into the atmosphere. And this system is working quite efficiently. But this system is also changing because the ocean current system is changing, the ocean temperature is changing, the ocean chemistry is changing. So methane was in a kind of equilibrium for some time. And during the last couple of years, we see quite a distinct increase in methane. Do not know where this signal is coming from. And at the present time, that, of course, is putting a pressure on the scientific community to give an answer to the politicians. What is going on with the methane in the atmosphere? Where is the methane coming from? What is presently becoming more unstable?
We have done some very comprehensive measurement campaigns where we have measured at the seafloor, in the ocean, at the sea surface and in the air at the same time to understand how methane is regulated in this whole system. There is a lot of methane stored at the seafloor, And this is so much that only a small change might impact the ocean or the atmosphere. The balance here needs a lot more focus, a lot more observations, and combining atmosphere, ocean, climate, different kind of competence together.
In my profession, I'm interested in studying methane cold seeps in the ocean, in the Russian Arctic, and also in the Barents Sea. It's, well, basically streams of gas bubbles rising from the seafloor, and those gas bubbles are mostly composed of methane gas. First, it's gas hydrates, that's solid form. It's basically ice-like structures. Also, the gas can be present as free gas, which is gas bubbles. Plumes of methane bubbles can vary. In some areas in the Arctic, we find gas seeps as tall as 800–900 meters. And the water depth in these areas a little more than 1,200 meters. In shallower areas, we often find gas seeps that are almost reaching the sea surface. The East Siberian Sea is definitely an area of concern for guys studying methane, in particular because it's so shallow there. So those methane bubbles have really high potential to get to the sea surface. Some areas, Spitsbergen, we find methane flares that are almost reaching the sea surface.
We have warmed the atmosphere to such a degree that we have hit the tipping point of a melting Arctic. We now face the potential for an abrupt climate change scenario. Current models predict we will shoot way past the Paris Agreement to 5 degrees and more, causing even more catastrophic tipping points to be activated.
Warming might lead to large injections of methane into the atmosphere. It's something we need to be concerned about. I would only add that it's one of many possible stressors. We move into a high-risk situation where we don't really have any experience. We don't know how to deal with it.
Permafrost and methane in general is of a great concern. And I think that this is something perhaps we need to pay more attention to methane in general in relation to the climate issue. My concerns are that there are great reservoirs of methane in the world, in particular in the Arctic. It is the risk of going beyond the tipping point where it will be difficult to go back and reverse the problem.
It's a very plausible feedback mechanism that in Arctic soils, permafrost soils, there's an enormous amount of organic material frozen, and the amount that is available there potentially to turn into CO2 and methane is maybe 3 times, 4 times all of the fossil fuels that we have burned. If we take all this material out of the deep freeze, you very likely get large CO2 and methane emissions on a huge scale over which we have no control.
I study methane emissions from lakes. We are in interior Alaska, and we are in discontinuous permafrost. The thing that we're looking at is microbial methane. This methane bubbling here behind me, it's dead plant and animal remains that were locked up in permafrost for tens of thousands of years. And as that permafrost is thawing, the microbes eat that soil carbon and they turn it into methane. This process of permafrost thawing and that thawing permafrost fueling methane production, and then methane escapes into the atmosphere, causes climate warming, which causes more permafrost to thaw. We call that a permafrost carbon feedback. It is a natural process. Our concern, though, is that as climate warms at a faster rate than it has in the last 10,000 years, that permafrost is going to respond by thawing a lot more quickly and releasing at a faster rate methane gas. Now, every time I go to a new lake, I attempt to light these gas pockets because it's a very high concentration of methane. It's highly flammable. We see a positive flame test when they contain methane. So it's a quick gas chromatograph on the lake to tell us, do we have a methane lake or are we dealing with a different kind of lake? There are many new lakes forming that were not here 30 or 60 years ago. And those lakes have 10 to 100 to 1,000 times more methane than the rest of the lakes. They are a picture of the type of methane emissions we expect to see in the next 10 to 50 years as permafrost warms and thaws, and that permafrost feedback cycle kicks in and really accelerates.
Now, is it methane? Is it permafrost? Is it the dissolved organic carbon in the ocean, which is suddenly remobilized? These things are all intertwined with each other. So really what one needs to ask is, are there positive feedbacks within the system? The answer is yes. So it just stands to reason, purely by common sense, the less you disturb it, the better off things will be.
We have the solutions at hand, but the question still remains. Can we mobilize and take collective action before it's too late?
There isn't the oomph in the world to do this. They talk about, with the Paris Agreement, how we must reduce our carbon emissions and to keep temperature rise at some low level. But in fact, of course, we won't be able to do that. The technology that can save us is something that will take carbon dioxide out of the atmosphere. So it ought to be obvious that the biggest research effort that man is involved in should be to develop direct air capture methods that work. And if we do that, then we can save the world, and so why don't we do it?
Direct air capture is machines which take in ambient air and extract the CO2 from this air. For the last 10 years, we have been working on direct air capture with the goal of making it with the least possible energy impact and ultimately with the best economics. This machine consists of 4 40-foot shipping containers and can be any size. There is no limit to it. So we take in the ambient air here, and inside we have our filter structure. We get the waste heat of the waste incinerator to drive this plant. Once the CO2 is captured, this gas is then going to a greenhouse, and this greenhouse is using the CO2 to increase the CO2 concentration in the atmosphere of the greenhouse, which is done already nowadays, but with fossil CO2, and from tomorrow on, they're going to use atmospheric CO2. This plant will allow to close a carbon cycle. So, of course, the CO2 goes into the greenhouse and goes to the tomatoes and cucumbers, and once we eat them, the CO2 goes back to the atmosphere. But since we recapture the CO2 from the atmosphere, it's a closed cycle. So this can be a missing piece of the pie in order to close a global carbon cycle in the energy or transportation sector. So besides using CO2 in a greenhouse like this, we can take CO2, we can take water, and we can take renewable energy. We can again produce fuels, for example, jet fuel. In order to capture 1% of global CO2 emissions, we would need roughly 300,000 of the plants behind me, which is of course a very high number. But if you compare this to existing infrastructures, it's a scale which humanity can handle. So it's definitely an achievable goal. The next project is to bring a plant to Iceland to capture CO2 from the air and sequester the CO2 underground. And in 2 hours, you literally turn CO2 into a stone, which stores it in a permanent and safe manner. In order to run the plant, we would use geothermal heat. There's an abundance of it on Iceland. Therefore, we would have low carbon footprint energy available to drive the machine.
So today is a very special day. We have brought CO2 capture plant up here to Iceland. And we're taking CO2 out of the air and then pumping it underground, storing it in the basalt rock formation within the Carbfix project. So we extract CO2 from the air and permanently remove it by turning it into rock. And yesterday night was the first time that atmospheric CO2 was injected into the ground. We can go up to thousands, 10,000, 100,000, and even up to millions of tons of CO2 per year that can be extracted from the atmosphere. That is actually, to our knowledge, the first time ever in the world that direct air capture of CO2 has been combined with underground safe and permanent storage of CO2.
Yeah, it's a new relationship with carbon. Why can't we find a way to make it an ingredient for something? Why can't we put it in our plastics or in our building materials? Or through the help of carbon dioxide chemistry, turning carbon dioxide into the things that we need every day.
I'm Daniel Nocera, the Patterson Rockwood Professor of Energy at Harvard University. These are my labs, the labs where we invented the artificial leaf and the bionic leaf. And what they do is a complete photosynthesis, sunlight, air, and water to fuels and food. Think about photosynthesis. If you think about what it really does, is the building block of life, and its building blocks literally are CO2, water, and sunlight. And we build all of this, like this, wood and food and starch and biomass. That's a remarkable transformation. This photosynthetic process, it's very complex, but we really listen to nature. And that we finally ended up doing in 30 years. And something that makes us really happy, not only can I say, yes, we can do it artificially, I can do it 10 times better than photosynthesis. We made special catalysts that coated the artificial leaf, and then they would split water to hydrogen and oxygen. The second part of the invention is the bionic leaf. It takes the hydrogen from the bacteria, and then it makes fuels. And so depending on what genes I put into the bacteria, I could have the bacteria make materials. They could make drugs. We've shown they can make fertilizer. We can work out of any water source, including natural waters, seawater. As long as you have my artificial leaf, you can do it in your backyard. We don't need to dig what's been down there and release more CO2. The artificial leaf, working with the bionic leaf, takes the CO2 out of the atmosphere, uses sunlight and water, and we make fuel. So we don't add any more to the atmosphere, any more CO2. And it's another issue because the cost I'm up against, the developed world has spent tens of trillions of dollars to build what they now use. It's kind of hard to walk away from a multi-trillion-dollar investment that you've paid off. So that's what it's all about. Therefore, you need policy and you need good partnership. And the public informing them that they have options and that there can be this different world.
This new world can be sustainable, innovative, and profitable. The green economy is creating millions of jobs and will create millions more. It matches and will surpass the economy of the fossil fuel industry. The challenge to reverse climate disruption opens up opportunity for everyone. It is now more profitable than ever to be green.
Up until recently, the profit you could make from creating the problem was greater than the profit you could make from the solutions. So the solutions had to be done with subsidies, which were rare, non-existent, or altruism, or faith. But people who were making the problems were raking it in, raking it in, raking it in. And I think we're at a crossover where actually the profit you can make from the solutions is greater than the profit from the problems. And that is not well understood. So it's not that altruism need not apply, it's a great thing, but actually altruism will not be needed in order to move towards a world where we reverse global warming because, in fact, it's less expensive. It's more profitable, more beneficial, more jobs. It's the most amazing thing that's happened in the last few years and is going to do nothing but increase as the years go by because engineers and designers and basically who are unknown and unnamed have been working diligently and are working diligently to reinvent a new way of being a human being relating to this planet.
In Orkney, we have a really strong maritime tradition, and since the 70s, the oil and gas industry in Aberdeen has been a major contributor to the local economy, providing tens and thousands of jobs. But really, in the last few years, we've seen quite a big downturn in terms of the oil and gas industry and the price of oil. But we've got lots of really experienced people in offshore operations on our doorstep, and they're finding new jobs in offshore renewables and companies such as ourselves. Tidal energy is almost an entirely untapped resource. We think we have the potential around the world for about 100 gigawatts of capacity, perhaps more. And what that equates to is low carbon energy for millions and millions of homes. What we've got here is the world's most powerful floating tidal energy generator. We've got a floating platform to which two rotors are mounted.
We start with the rotors turning, which produces the electricity, which comes back up into the machine where it's conditioned, and then it gets transformed and stepped up and fed back into the grid.
It's like a wind turbine on its side with two rotors instead of one.
2 weeks ago, we had great success. First period of 24-hour continuous generation from the device. It actually operated beyond expectations. The device itself generated over 18 megawatt hours of power in that 24-hour period. We're converging on more traditional methods of renewable generation and really putting tidal out there as a real competitive technology across the world and the world's generation needs.
The tidal turbine it's 63 meters long in total. We do all the power conversion within the device itself, and it's ready then for export right into the UK electricity grid. So we're aiming for tens of thousands of these tidal turbines. We've got this fully integrated system for producing low carbon energy, so we're very excited about it.
So EMEC was set up as a testing laboratory because we know that there's a huge amount of energy in the oceans all around the world, and we're trying to find a way to harvest it. And so we realized that one of the most important things was to have a test center which would allow us to find out how to do this properly. And so what we've got is a site here where we've got cables that are out in the sea that allow developers of these machines to put these machines onto our cables, and the electricity is then brought onto shore, and that then feeds into our national grid. So this is real. This is making electricity out of seawater. So at the moment, we've got a device called the Penguin, and that's by a company called Wello Oy, and their machine is effectively a large pendulum inside a ship, and as the ship moves, so this pendulum turns horizontally, and that then generates electricity. The sea is unrelenting, and it will really try and damage equipment. So making equipment that's reliable, robust, efficient, cost-effective. All these things are the things that people are grappling with. But the really clever thing, because we have done that piece of alchemy, we've actually turned seawater into electricity. And that really is huge, because people have worried about whether you can do this or not for years, and we've just shown you can. And that's a big step forward.
No one can say that the scientist has not warned, has not told that we have to reduce the emissions of greenhouse gases. That should be clear to many.
How much farther can we go? How many more tipping points can we go before we hit a tipping point from which our civilization cannot recover, or from which the life of this planet, or a large portion of the life of this planet, cannot recover? We cannot allow ourselves to reach those points, and we're so damn close to it.
We're at a turning point. Either we can stay the course and drown, burn, and starve ourselves to death in the face of the climate crisis, or we can come together, we can innovate.
Where do we stand? Is it possible? Is it game over? Or is it, in fact, game on, which is that we have at hand the ability, capacity, and solutions that can reverse global warming, not mitigate, not reduce, not stabilize, but reverse. When you make your goals bigger, it opens up possibility. It opens up imagination. It opens up innovation. It doesn't foreclose, it actually does the opposite. And so it's not that there's one solution, but together you can achieve drawdown by doing 80% of the solutions. Every one of them has so many cascading benefits, makes a better world for everybody. So we don't lose by understanding the climate change is happening and responding to it. So what's the problem?
We are the first generation to see the advance of climate disruption and the last with a chance to fix it. In spite of all this evidence, we are currently burning fossil fuels at an ever-increasing rate. We have heard from the scientists who have told us the truth based on actual research. It is time to end the delay, to listen, and to implement the solutions at hand. Time is running out. The ice is melting. Decisive action must be taken now. There is no other option. This moment is within our reach. Let us grasp it. It is up to us, each one of us, to save this unique blue planet for generations to come.
not watching, I'm not doing wrong. And hope and rain and ice is burning. Then you see us turn on a friend. Will you hear them calling again? Lord, the world ran dark, the wave came crashing. If we're all gone, will you still carry on? If love is light, but ice keeps burning, will you see us ride to the edge? One last fall from your hand. Dear Lord, if you don't want me, I'm not staying. Love is light, light keeps burning in. Let me know if I'm worth saving. We're almost gone, so if we fall again, will you carry on? If we're falling in, will you catch us up? Lord, just let me know if I'm worth saving.